University Catholic of Leuven, where she is now back in Belgium. She spent 9 years working for the ISP in Japan, IIG, and NTT, and she holds a chair in embedded systems at UC Leuven, University Catholic of Leuven, where she is now back in Belgium. She spent 9 years working for the ISP in Japan, IIG, and NTT, and she holds a chair in embedded systems at What's going on? I was hearing myself again.
I heard you twice, but
yeah, that's pretty bizarre.
Shall I start?
Well, that was a double introduction. I have no idea how that happened. Were you recording, Nishant? Maybe that's why. Maybe you were live streaming at the same time. Well, anyhow, Cristel, the room is yours.
Okay, so I've chosen to talk today about multi-constraint paths computation using segment routing. So how do you compute paths, and then how do you deploy them in segment routing? And the next part is about how you detect detours. So there is a computation part and then a measurement part to my talk. And both are related because when you compute constraint paths, in fact, you build detours in your network, and this may have an effect globally on the connectivity. So this work has been done with collaborators that are mostly in Strasbourg, because I just moved from Strasbourg to Louvain. And so you can find more information in these papers. So first of all, I'll talk about how to compute constraint paths for segment routing. So what you have usually is that you have operators that will use a routing protocol and configure it with weights on the links to reflect some properties of their network. So for example, here you have the IGP cost who reflects the bandwidth along the links that you have in the network. And this is part of the GEON network. So what you can see here is that the lowest IGP path is in green, and it has a cost of 3. And then you have another path that goes via Budapest that has a cost of 4 because it has a little bit less bandwidth. And then finally, you have another path that is more direct, but has a cost of 10 because it has even less bandwidth. And so the point here is that when the operator sets up the IGP cost, he has in mind best effort traffic. But more and more, you have other additional services that arise. So for example, you have gaming and cloud gaming, which usually require less than 20 milliseconds delay. And then you can have other applications like virtual reality, where you even want less delay in the order of 20 and between 20 and 5 milliseconds. And then you can also have 5G services where you can personalize different slices with different delay constraints. So the objective is to both try to enforce the IGP cost as much as possible, while still respecting the requirements of these different applications. So behind this work, there is a set of assumptions. And the assumption is that for this traffic that we want to, that has very strict constraints on the delay, we assume it can be prioritized, and we assume it can meet the minimum propagation delay. So why do we do this assumption? Is because we will measure delay, we will keep the minimum delay observed, and we want this delay to be very stable across time, such that we don't have to redo the computations, and we don't have to build our data structures too often, because this is costly. So assuming these data structures are quite stable, how do we compute paths efficiently? So why do we focus on segment routing? Segment routing has been around for a few years now, and it's been standardized and being deployed by ISPs. And so it's been demonstrated to be easier to deploy than traditional MPLS technologies. So that's why we focus on this. If you want to deploy segment routing, it's a bit lighter in the network because you have to maintain less states in the routers. So with segment routing, what you do more or less is you do source routing. So you have the possibility to, in the packet, to add some information to say where the packet needs to relay. So for example, here, if you want to use the yellow path, you can say in the packet that you want that the intermediate destination is Budapest, and so your traffic will go to Budapest. And then it's decapsulated, and then it finally go to the final destination, which is Vienna. And so what we do here is that the routers will perform a set of measurements, and then they will monitor the RTT among the links that are directly connected to them. And this way we're able to have for each link, in addition to an IGP cost, we have also a minimum delay. So for example, here you have 3 sets of minimum delays, depending on the paths that are taken. And assume you have an 8 millisecond constraint, then here, if you want to have a min IGP cost pass with respect to certain to this delay constraint of 8 milliseconds, then the pass you will want to use is the yellow pass via Bucharest. So the problem we are trying to solve is computing delay constraints least cost. And this has been shown to be NP hard. In addition, because we have segment routings, we will have some constraints. And the main constraint is that because we store it's source routing and we store information in the packets, we have a limit on the number of segments and the number of intermediate hops we can store in the packet. So DCLC is NP hard. And then we have additionally, sorry. Okay. We additionally have some constraints on the segments, but we will take advantage of these constraints. So first of all, if we have this simple network on the left, and you want to compute a pass from node 1 to node 3, we have now a graph where we have 2 metrics on each edge. We have the IGP cost first, and then we have on the other side, we have the delay experienced along the link. And so if you want to compute the least cost delay constraint pass, you'll have to compute a set of possible paths and to determine which one meets your constraints and which has the least IGP cost. So for example, here you have multiple paths between 1 and 3. The first one is via 2, and this one is taking the interface A on node 2 and will have a very high cost, so a cost of 11, but have very low delay, as you can see on the graph on the right. Now there is another path that is possible, that is via the interface B on node 2, which has a lower delay and higher delay and lower cost. And finally, you have another path that is the direct path, which has a higher delay, but lower cost. So all these 3 paths are not dominated, and you'll probably see where I want to go is that you have to maintain a Pareto front of the possible solutions, because then if you want to extend this path and go to node 4, you can see that now the path C, which was the direct path between 1 and 3, is not viable anymore, because when you add the delay, which is 1 more millisecond, you will reach the delay constraint. So we have this these non-dominated paths, which consist of the Pareto front, and we have to maintain this front. The good thing is, so a Pareto front is heavy to maintain in practice, but we are doing was trying to solve a real problem, which is finding delay, well, paths that meet a delay constraint. But we know that when we measure the delay in a network, we have some inaccuracies, right? We have some measurement artifacts that make us not be able to measure paths with an error below than 1.1 milliseconds, 0.1 milliseconds. So in fact, we don't have, it's not a continuous problem. We can sample the delays, and we can in fact only keep one solution for each interval within our error rate, which makes us having a slower Pareto, reduced Pareto front to maintain. And then, because we have a delay constraint, we have a number of paths that are possible, a total number of feasible solutions. And so this also makes our problem bounded. So while the problem is NP hard in practice, because we can discretize the delay, because we have a strict constraint on the delay, we can have a bounded Pareto front, which makes the problem a bit simpler. But then we have this physical constraint that we have to also enforce, which is the number of segments that you can have in a packet. And this is limited because when a node has to process the header, he can only process a certain number of bytes at one point in time. And so to explain a bit how a segment routing works, so here you see on the right the segments that are used to reach node 4 from node 1. So first of all, we will tell the packet to go to 2. And then there we can decide, because we have 2 adjacencies, we can decide on which link we want to send the packet. And so here we'll select adjacency A. So it's the segment 2A. Finally, when we arrive at 3, we'll select the adjacency 3A to arrive at 4. So this is the path that was computed in the previous slides. So the maximum segment we can store is called MSD, and it's one more constraint. So we could think that we'll have, instead of having a 2-dimensional Pareto front, having a 3-dimensional Pareto front. But we, to avoid this, we come up with a data structure that we call the segment graph. So we'll build an alternative data structure that is based on the segments. So we will pre-compute the segments and their properties and build this graph. So how do we do this? Well, we compute an all-pair shortest path with some additional tricks to take into account that we have the delay on the path on the different segments, and also the fact that in a network we have equal cost multipaths. So this is very important because it's a bit tricky that we have to deal, because we don't specify the exact path that the packet will be following. In most networks today, you have equal cost multipath, so you have to assume that when you don't specify every hop between 2 nodes that are distant, you can use multiple parallel paths. And in this case, we assume, well, in the segment graph, what we do is we consider that the delay is the maximum delay you experience between the 2 nodes. So for example, here, from 1 to 2, you have a segment with the properties of the direct link. So this is what is shown in the graph here. Then if you go from 2 to 3, you have another segment that will be the segment with cost 6. So it goes, it's the adjacency B, and then it's finally the link between 3 to 4, the adjacency at the bottom or at the top. And then we do for the delay is the sum of the delay on the 2 edges, and we take the maximum of the 2 available paths with having a cost of 6. Then from 3 to 4, this is quite easy. We have a direct link with one property, which is a delay of 6.6. And then we have here parallel links, and the other link is not dominated by the segment we previously computed, so we need to add it also in the segment graph. So we do this for all pairs of source destinations. And so here you can see between 2 and 3, we also have 2 possibilities, and the paths are not dominated, so we need to keep them both. And so this means that in the end, we have a full mesh with some parallel links in addition. So what are the properties of this graph? Is one edge in this graph is one segment that you will use and have to store in the packets. And because we have a limitation on the number of segments we can have, exploring this graph using a Bellman-Ford algorithm makes it possible to stop when we reach the maximum segments that we are allowed in packets. And this means that this is the best solution we can achieve in practice in this network. And so this makes it bounded. This bounds the computation time. So also an advantage of using Bellman-Ford's family of algorithm is that we can parallelize the exploration. So when from an edge, you have to discover all the possible downstream nodes, you can parallelize this. And so this makes it computationally feasible in servers, like when you have a control server that will compute the segments and the path, the end-to-end path for the network. And then we found a way to deal with a 3D Pareto front in a much more lightweight fashion. So how does this work? You have this way of, so this flow, where first we retrieve the Pareto front of the previous iteration. And then for each node, we extend the distances by exploring all the segments that go out of this node. And we can do this in parallel. Then we clean up the Pareto front. And the complexity of this algorithm is on the order of the maximum number of segments you are allowed, times the number of edges you can have in the segment graph, times the number of paths you can explore, given that you have a maximum delay possible, and at the granularity we explore the path. So this means we can compute the least cost delay constraint path, and we know that the delay will respect some guarantee that depends on the error we have in the measurements when we probe for delay in the network. So now we've compared this approach to the existing and the mostly known algorithm in the space, which is SAMCRA. And so you see that, so SAMCRA is Dijkstra based, so it's not easily parallelizable. And we compare it with our algorithm, which we call best to cop, and we do, here it's 1 thread versus 8 threads. So in blue it's 8 threads, and you can see that with 8 threads we reach, we can compute for much larger topologies. First of all, we go up to 10,000 topologies, 10,000 nodes topologies. Here we do it on random graphs with random metrics to be hard on the algorithm. And so you can see that SAMCRA takes much longer to achieve the computations. We also run the algorithm on topology from a tier 1, where we have the IGP metrics and the delays. And again, we can see that our proposal works better. What I have to say is also SAMCRA, because it's Dijkstra based, is very sensitive to the density that we have in the segment graph. And so that's the reason why it does not perform so well here in this case. And then because the purpose is to deploy this in much larger topologies, we expect that in 5G topologies we'll have a much larger of nodes. So we try to push it even further, where we generated artificial topologies but that try to mimic real properties of networks. So if you want, you can look at the paper if you're interested in using this generator, and also to critique the generator and see what works good and bad in that generator. So, but what we do is we take different topologies, and then we try to use the roads that exist in the different continents to get the delay, because we assume the links are deployed along roads that exist. And so on these topologies, we see that we are able to compute our constraint paths in reasonable times. And the last topology you see is 100,000, more than 100,000 nodes. So what we show here is that we have an algorithm that is adapted to segment routing. We can reach very large networks. It's parallelizable. And so it's also, we can provide some guarantees on the paths that we obtain in the end. So we have extensions of this works, which I don't present here, where you can do this and you can improve or adapt SAMCRA to reach the same performance. So this will be presented Monday by the PhD student who will defend his thesis. So this will be published also very soon. But now, so because you have this possibility with segment routing to deploy constraint paths, and because the computation now is more lightweight than it was before, we can assume it will be deployed more and more. So the question we try to ask as well is, these type of paths, will they be deployed more and more in the internet in real? And so we have some preliminary results that I will present now on how to detect when you have detours happening in the network. Because what you saw here is with segment routing, you tell the packet to deviate from the normal, the shortest IGP cost. And this can have some impact. Here it's a intended deviation, but sometimes it's not intended. And even sometimes the network operators don't know it. So we try to determine, to develop a methodology to detect these cases such that the operator can then look and see whether it's intentional or not intentional. So the assumption is that inside an ISP, you will follow by default the shortest IGP path, because that's the way the routing works. And so what we do is we use trace routes to probe inside an ISP. So for example, here we have multiple prefixes that are outside the ISP. So they are behind T. And we send 4 trace routes for each prefix, for each /24. And we look at the route that we observe in trace routes. And so if inside the ISP, we observe always the same routes, then you can see here, each trace route is a dot. And so for each prefix that you have here in lines, you see a single route. So the columns are the routes and you see a single route. But as I said before, in many ISPs, you have load balancing, and load balancing can be done at various levels. And often it's done at the IP level, which means that if you probe 2 IP addresses within the same prefix, you may observe different routes within the ISP. So this is a normal behavior. I'm sorry. And so, for example, here you have 2 routes, and you can see that if you probe with sufficient trace routes and a sufficient number of IP addresses, you will discover these 2 routes for all the prefixes that cross the ISP. And so now another normal behavior is that for some paths, the operator will want to do some traffic engineering. So it may be using segment routing, as I showed before, or using MPLS. And for these, we expect that it will be done on a prefix base, or we are mostly on a prefix based. And then for all the trace routes towards this prefix, you will observe the same paths. We assume that this is the exception compared to the load balancing case. And then a forwarding detour, more or less, looks the same as a traffic engineering. So it's a path that does not follow the shortest IGP route. So your traffic does not follow the shortest IGP route. And we want to detect these cases. So it may be traffic engineering or forwarding detour. Our aim is to detect when it's problematic, so when it's predominant in the network. So why do we want to detect this? I already said this a bit before, but forwarding detours, they can happen because some routers lack some routes. And this may happen because some routers don't have enough memory, and so you have some prefix aggregation inside some ISPs, and the aggregation does not happen at the same level on all the routers because they don't have the same amount of memory. And then it can happen for other reasons, just a router that had a bug and is dropping some of the routes, some of the announces. And it can have a negative impact on performance because it's not the shortest IGP cost, so we assume it's not the desired part from the ISP. Of course, when it's traffic engineering, it's desired, but in some cases, it's not traffic engineering. So how do we detect them? So first of all, we will probe two types of destinations. We probe destinations that are outside the ISPs. As I show here, all the prefixes are outside the ISP. And then we probe also the IP addresses we discover for T, for the exit node of the ISP. And so we have two examples here. You have an example where you have forwarding detours and traffic engineering in the example 1, which are the exception. And on the example 2, you have forwarding detours, which are more common. So you observe it for a lot of the prefixes that are probed. And so the cases we try to detect are the cases of example 2. So first of all, we try to determine all the prefixes that use the same route. So we will group all the prefixes that see the same routes. So in the example 1, we will group all the red prefixes because we discover all the same routes. And on the example 2, we'll group also all the purple ones. And then we check in which group you have also observed. One of the routes is the route you observe when you probe the exit of the AS. And so, for example, here in the example 1, the exit is observed in a set of routes for prefixes P1 to P8. And so this is assumed to be the normal behavior. While in example 2, the route to T is also route 1 and route 2, and it's the one observed for prefixes P5 and P6. And so this is the normal behavior, while all the others, even if they are more numerous, are the behavior that is not expected. Because the reasoning behind this is that when you target an internal destination, so T is an internal destination, because the router has less information to maintain for all the routes internal to the AS, he will have the good routes for this. But what happens is you have problems when you have destinations outside the AS, because you have this interaction between the IGP and BGP. In BGP, you have many more prefixes to maintain, and often these are the prefixes that get aggregated or dropped by some of the routers inside a network. So here you had the two load balance paths, and these are the regular paths. And so these are the paths that you see here in red also. So we count the number of prefixes we have in each set. The one we mark in red is the legitimate set. We assume it to be the legitimate set. And then we count the proportion we have in each set. And we only consider it a forwarding detour when we see enough prefixes in the set that is not legitimate. so that is not the red set, and for which we observe many prefixes inside the set, so the majority of the prefixes. So for example, here we'll conclude that we have forwarding detours in the example 2, but in example 1, we have some doubts because we have also the traffic engineering prefix, and we cannot distinguish the traffic engineering, which is like a small event, to a forwarding detour, which is if it's also a small detour impacting a small number of prefixes. So here we will only detect example 2. And why we do this? It's because we want to be conservative. We don't want to raise alarms and to say to determine and to say too many times that we have forwarding detours, while it can be just a regular traffic engineering. And we know many operators deploy traffic engineering at slight doses. So we only want to detect cases where we have very suspicious events. So what are our experiments? So what we did is we used the NL ring. So I don't know if you don't know NL ring. It's a set of nodes. It's Linux machines that are managed by network operators. And then if you get access to them, you can start probing from all of them. And what we did is we took a sample of 100,000 prefixes and we performed our measurements. We kept only ASs that we are able to cross sufficiently enough, because otherwise we don't have a sample good enough to make some conclusions. So here we consider an AS in our data set only if we cross it for more than 100 prefixes. So in the end, we study 54 ASs. And out of these 54 ASs, we find 25 where we have some forwarding detours. And what you can observe in this figure is that, so first of all, on the x-axis, you have the number of ASs. And on the y-axis, you have two scales. On the left y-axis, you have the fraction of couples that we measure for which we detect a detour. And on the right, you have the number of detours the number of couples in the AS for which we observe the detour. So for example, if you take the AS 2914, you can see that we measure a large number of couples, and among these large number of couples, we found a limited proportion of these couples that have detours. And so the conclusion here is that you have these ASs, and so half of them experience some detours, and we are conservative. So for half of them, we believe something strange is happening. But when it's happening, it's only for a very limited portion of the source destinations we're able to measure. And then we looked a bit more deeply into the results, and to try to understand if when we see forwarding detours, because I said we only look at big forwarding detours, but we wanted to understand, do we see small forwarding detours that may, so like traffic engineering and things like that, that we may have discarded, but they're very common. To try to understand if being conservative make us miss many things that may be interesting in the future. And so what we observe is, in the end, when we have forwarding detours, in fact, most of the cases, when we look more deeply, it's a lot of prefixes that are impacted. But as I said before, it's only a few source destination pairs inside an AS that will experience this behavior. So the current question is, will this behavior increase in the future with segment routing becoming more predominant, and with also some techniques like, for example, you can use segment routing to determine which exit point you want to use in your AS, and you can eventually use different exit points that the ones that are advertised in BGP. So are we in the future going to see more and more cases where in fact the traditional routing paths are not the legitimate, are not the ones that are mostly seen, but we'll see many more of the other types of paths. So what I've shown here is that it's possible to compute at scale constraint paths with constraint on the delay and respecting minimum IGP cost, while also being deployable in ISPs today with the constraint we have with segment routing. And then I've also shown that we have some preliminary heuristics to determine when we have forwarding detours in networks. And so thank you for your attention. And so this work has been done with these people at Strasbourg University and also people in Napoli. And I'm open to questions.
Thanks, Cristel. Questions from anyone? I had a clarification questions. I think at some point you were mentioning when you were generating your those networks with the violin plots, I think, and then it sounded like you said 100,000 plus nodes in 5G networks. Is that something that you're hearing from operators and can you also do routing over those several over 100,000 nodes, or is it internally 100,000 nodes, but you can't really see most of them?
So I'm trying to get back to it, but yeah. So what we know is that there are some operators deploying networks up to 10,000 nodes at the moment in Asia. There is an IETF draft on segment routing where people state that they want to reach 100,000 nodes, and with some names of operators that are almost at that scale. And so, yes, there is a requirement, and that's why we pushed it that far.
Wow.
So that answers your question?
Yeah, thanks.
And so because there is no topology available today, that's why we
you have to generate it.
Yeah. And we tried, because we know here we tried, the delay is the propagation delay mostly, that people who implement segment routing, when they want to do delay constraint paths, they measure the delay and they keep the minimum delay, so it can be it's an approximation of the propagation delay. So that's why in our generator we use roads to simulate where the links would be and to have a distance and to get the propagation delay between two cities or 2 points, two routers. Yes.
Okay. See, two people have their hand up. Mace.
Yes, thank you very much. Thank you, Cristel. It's quite interesting. So I was actually going to follow up. I have I have a few questions, but I'll limit to two. One is particularly about this graph. So you're dealing with the propagation delay, but also you're exploring ultra large topologies, actually ultra dense topologies. And the thing is in here, I'm sure you're aware that the relationship between, because distance with this large number of, with these dense networks, distance becomes shorter. So the interplay between transmission latency, switching latency, and propagation latency becomes sort of a trade-off. And I'm wondering, have you looked at this trade-off? Because sometimes if you're looking at 45K or so, or anything, then you're dealing with a metropolitan, with distances where propagation delay may be not so problematic. So what are your thoughts in there?
Yeah, this is a very good question. So when you have, it means you have many more equipments, and more or less, the more equipments you have, because it gets dense, the more time you will spend within the switches rather than transmitting the packets, right? So the way it currently works is that routers only measure or try to estimate the propagation delay. So we don't have this information about the, the switching delay, which I think should be included in the model, but it's not the case at the moment. So we don't have an idea of this. But we have the number of segments we use, which is bounded, but still this is not representative of the total number of hops that you have along the path. So I don't have the information about how many hops. We should look at this, how many hops are really crossed, and so by how much the delay could have deviated because of switching delay.
I mean, I'll be happy to communicate offline because we've done quite a bit of work on modeling that switching delay with a couple of things gone off. So I'll probably leave it there if you haven't modeled it. My other question is more about the detours. So it's quite fascinating to look at, and there isn't any real clear indicator, black and white, that tells you this is a detour or not. But from the ones that you picked up, are you having some analysis on the distribution of detours? Like what I mean is that, like, things like what are the minimum, maximum, kind of like distribute. What do the detours look like? And how severe are they?
So we looked at a few of them. And so I can give an example that was not shown in the figure here, but that triggered the whole story, is that we had a provider in France where we had partial routes, but not partial routes in that we had a default route. We had some of the peering routes were in the routers, but not the transit routes. We only had one transit. And so the side effect was that we had these packets leaving Strasbourg and going to, well, they were supposed to, according to our table, they were supposed to go to Paris, but then we saw them going out in Marseille, and vice versa. Some packets that were supposed to go out in Marseille were in fact leaving our provider in Paris. So, but these are corner cases. We don't know how much traffic is affected because we only look at routes and not the traffic. And then when we looked at the operators we have here, we tried to discuss with some of them, but often we had a hard time communicate with the right person that was able to have a view on all the routers. So we were able to discuss with some of the researchers where they also looked at it and said, yeah, this is not normal. I try to find out what's happening. But if I show the graph again, so we don't have a read for the cases I have on the figure. I'm sorry, the animations are not very practical in this case. But so, for example, we have here you see the fraction of couples that we measured where we experience forwarding detours are very small compared to the total number of fractions we measured. Okay, and within there it was also a limited number of prefixes that were affected for our study, but it was still, more. So here, for example, often you had around 10 to 20 parallel paths, and so you had for one of the paths more than 1/20th of the prefixes that were carried on these paths.
I see. Okay. Okay, yeah. Thank you very much.
Thank you.
Thank you, Cristel. That was very interesting. I'm a little bit confused because the first part of the talk seemed to indicate that forwarding detours were a good thing. And the second part of the talk seemed to say these are bad things and we have to detect when they happen. So I'm a bit confused, and maybe it's just my misunderstanding.
No, it's totally right. So we assume they are good, but they should not happen for the majority of the traffic. And also the assumption for computing these paths is that you need to have enough lay room because the delay has to be stable. And so in fact, when you do these segment routed detours, you need to do it for a limited portion of the traffic. Otherwise, you're not able to meet the constraints that you're measuring, because if you put too much traffic, then the delay will vary too much. And because we compute this segment graph based on the delay, if the delay varies, then all your data structures need to be updated too frequently.
But in the case of this slide we're looking at right now, we don't really know what. I mean, let's just assume they're doing this intentionally. Maybe they're solving problems that we don't understand. They're solving other problems.
Yes.
Some contractual problem or something like that. So they might not be solving the problem that you're trying to solve, in other words.
So here we were looking at this because we were assuming, so we had this problem with our provider doing weird things with our traffic, and we wanted to understand what they were doing. In some cases, it may be completely legitimate. And if I contract with my operator to say, send this traffic there or there, and I have this preferred exit point, then it's completely legitimate. But in some cases, and maybe, we experienced it and we assumed other people may experience this as well as customers, is sometimes you don't ask anything from your operator and you observe that the paths you get are not exactly the ones that you were assuming you get. And so it's mostly for these types of situations that our technique is targeted to. Of course, there are many things operators can do. These protocols, you can play them in a lot of strange ways. So we cannot predict everything what operators do. And so it's also a moving ground, but we're trying, and that's why we try to be conservative. But we give the means for people, if they are seeing something strange, they can try to confirm it with the data using our technique, and then go to their providers and say, hey, I see something strange. Can you explain this to me?
Oh, I see what you're saying. Okay, great. Thanks.
Any other questions from anyone?
Maybe a quick question from my side, Cristel. I was wondering, so one of the main issues that you have is that if things are changing dynamically a lot, it's problematic to compute, right? So how do you handle a situation where that's precisely the case? I don't know, there are path oscillations, things are changing very fast.
So for the constraints inside, so the path computation inside an ISP, we're focusing inside an ISP. So there we assume that it's not changing too much. Of course, an ISP can play with the IGP cost. And when you do this, you need to do some recomputation. For the world to not change too much, that's why I said we assume the delays are not changing very much, and we do the propagation delay, because this is supposed not to change too many times unless you go and change the physical topology, or you reconfigure your fibers, and your layer one path to go somewhere else. So of course it will change, and in this situation you have to recompute the segment graph, and it's an all pair shortest path, so it's a bit heavy. But the thing is, we assume, and that's the approach that is taken by vendors, is that these are done in, they're not done in the routers. They are done by a computation server that will update these data structures. And so this saves it a bit. And then, the more and more we see that operators don't play so much with the IGP cost. They play with MPLS and things like that to do the traffic engineering and the traffic steering. So we assume IGP costs are quite stable as well, but this is not so much an issue. The delays are much more of an issue.
Great,
And
thank you.
I think there is still work to be done in there to face with the fact that more and more you will want to also tackle other types of delays and changing delays. But this at the moment we cannot deal with that.
So also to get this, I think you said you're using something that you said the NL ring. Is that the NL nog ring?
Yes.
Can you say a bit about how you got onto it and whether you had any difficulties from the university side? Because some of the centralization of university infrastructure, at least in the universities I've been used to, makes it kind of difficult to get a node with outside of the firewall and things like that. So just curious about your experience.
Yeah, so for this, I've been lucky to not have too many problems with firewalls at universities where I was. And so NL Ring, in fact, it's managed by operators, and I've been working for operators before. So I have some contacts with people who manage ring nodes. And then so I asked to have access to the ring, and then you just SSH into it, and then you launch a command. So usually from a university you can use this, but you need to have someone within NL Nog that approves of your request. So we contacted Job Snyders to explain what you were doing, and so we to do the measurements we ramped up progressively to show that it would not kill the system. And so, yeah, this is not something we did like this. We had some negotiation phase and some explaining to do first.
Interesting. Thanks. Any other questions from anyone?
Maybe I can ask if no one else has.
Yeah, go ahead. Yeah.
So can I just follow up? So when you're doing the segment routing graph, are you looking at both the internal topology, the internal IS IGP, as well as across ISs, or is it across ISs only?
No, it's inside an IGP. And for the bigger ones, the ones that are up to 100,000 nodes, we divide the topology in areas. So we have a way, so we do multi-area, and we have a way to compute partial segments inside each. And so we divide the problem inside each area. But we assume it's an IGP, so we have the shortest path possible, and we know, so each area computes the segments to get out of the area. And then you have to do a, I'm trying to find the name in English, but you have to do a cross product to compose all these segments to get the ones that fits your request.
And so then an entire area is an ingress-egress combination. So if you have multi-links, the ingress-egress point of it, this is transiting through one area.
Can you rephrase a bit? I'm not sure I understand.
So because normally that's how we deal with interdomain, is that the area itself just looks like a multiple links with an ingress-egress points. So if I understood correctly, then you are calculating ingress-egress links segments with particular delays for that particular bubble, for that particular area.
Yes.
Right. Okay. And so I assume then your topologies are naturally converging to scale-free, or are you considering other topologies?
At the moment, we only consider these ones. So we only consider that we have, maximum for any given source destination pairs, you have maximum 3 areas to cross. Because we assume we are inside a big ISP, and then if you have a big ISP, usually in OSPF, for example, you have the backbone area, and then you have the stub areas, and we assume this model only.
Okay. And can I ask also, in terms of so this will be my last one, in terms of the detours, how much did you notice anything about the idiosyncrasies of routers? Because you mentioned, for example, they could have different memories, so they aggregate routes differently, and that has an impact on detour. Have you correlated the distribution of detours with potentially some knowledge about idiosyncrasies of some routers you monitored?
So I think this is true. There is some particularity on the routers that make it generate detours, because we only observe it for a limited portion of the ingress-egress edges we probe. So there is one node inside in the past that has some particularity, but we did not, because we did not get enough information from the ISPs to figure out what was causing this. So we know in some situation where we had knowledge that it was a memory issue, and we knew how they were selecting the routes they push in the router. But for the ones I show here, we don't have really this information.
Mm-hmm.
But we assume it's a property of the router, because otherwise, if it was widespread, we will see this much more frequently in measured ISPs. So it's not a global behavior. When it's in an ISP, it's not a global behavior. It's very specific to where you enter this ISP.
Hmm. Yeah, this could have quite an impact on how the detours are being observed.
Yes. Yeah, so this study is, you know, a point is in space. We use NLNOG. We measure 54 yeses. It needs to be done at a larger scale to draw broader conclusions.
Thank you. Thank you very much.
Thank you.
Excellent. And that brings us right up to the end of the hour. So let's thank Cristel for her fantastic talk. And have a good weekend, everyone.
Thank you for having me.
Thank you.
Thank you, Cristel.
Thanks.
Thank you,
Bye.
everybody.